Okay, so let's take a quick recap of previous session. So we have seen all the definitions related to relative acceleration before this. So now let's look at more applications based on that. Okay, now one important application of relative motion we'll see today is that if we are looking at the motion of two projectiles, that is two particles which are projected to move under gravity, then their relative motion is such that there is zero relative acceleration because both of them are having the same acceleration with respect to ground frame, which is the acceleration due to gravity. So solving the motion of one particle with respect to the other or relative to the other becomes very easy because there is no acceleration involved then. So let's understand that as an application. So relative motion of two projectiles two bodies or particles moving under the action of gravity. So the general idea is that if we have projected a particle A with an initial velocity u1 at an angle alpha, let's say, and we projected another particle B simultaneously like this, both projected at t equal to 0, then at any particular instant of time, see that we are using this system of axis. Acceleration of A is equal to acceleration of B, which is equal to the acceleration due to gravity vector, or minus g j cap. So that means the relative acceleration of A with respect to B, or B with respect to A, whichever one we choose to take, is 0. So they have 0 relative acceleration. So this implies that the relative motion of A with respect to B or B with respect to A, whichever be the case, is a uniform motion, or one with 0 acceleration. Yes, Kirti, that's correct. So uniform motion. So this aspect makes solving the relative motion very easy. Okay. So therefore, okay, so let's understand this with few examples. But this is a general point that you should remember from this point onwards. Okay, that if we have two objects that are moving under the action of gravity, it's always going to be easy. Generally speaking, it's always going to be easier to solve the problem using relative motion, because the relative motion is unaccelerated, or is a uniform motion. Okay, so let's understand this with some numerical
Scholar.
example. Yes,
Yeah, please scholar. That's a
yeah.
little bit right. So done.
Okay, so we'll start with an example in which there is vertical motion involved. Okay, so straight line motion under the action of gravity. But eventually, we'll also see the next problem with greater degree of complexity. So this guy drops a particle A at time t equal to 0. And right under where A is present, another person projects ball B. At t equal to 0, such that this height difference between A and B at t equal to 0 is h. So given that this height difference is 20 meters, okay, and the projection speed is also 20 meters per second, and acceleration due to gravity is 10 meters per second square. So actually this will not really be required. We have to find the time t and the position at which A and B collide, and preferably do this by solving the motion of one with respect to the other. It is relative to the other. Okay, so just try this out. We'll discuss in a moment. Okay. Very good. That's correct, Kirti. Okay. So one way to solve this problem, so one thing you have to be careful when you are using relative motion is that you must use the common reference frame for both the objects A and B. You cannot say that, okay, I have a different reference frame for A and a different reference frame for B. So we have to use a common reference frame. So here I'll take that common reference frame such that y-axis is upwards and x-axis is like this. Okay. So with respect to this common ground frame, initial velocity of A is 0. Initial velocity of B is 20 j cap with a plus sign in meters per second. Okay. But more importantly, acceleration of A is equal to acceleration of B, which is equal to minus 10 j cap in meters per second square. So this tells me what? That the relative acceleration of B with respect to A or A with respect to B, whichever, is 0. As this tells me that the initial velocity of B with respect to A, that is also 20 j cap. So that means in A's frame, or we can say relative to A, B has a uniform motion with relative velocity of 20 meters per second upwards along y-axis. So that means B's displacement with respect to A is 20t upwards. So when this relative displacement becomes 20 meters, then they collide. Okay. That's it now. So 20t should become equal to 20. So t should be equal to 1 second.
Sir,
So,
Yeah.
so we can use the height method also, right? Like A travels X and B travels 20 minus X in the same time.
Yeah, we can do it that way also.
sir, how did you
In fact, yeah.
So, can you explain an assumption? How did you get to SBA is 20 meters?
See where B is starting from. You're in A's frame now. No. Imagine you're sitting on that particle A. So B is starting from a position below you at 20 meters now.
Yes. Sir.
This is where B is at t equal to 0. This is 20 meters below. And at whatever time the collision is happening, B is now reaching you. No? So what is the relative displacement? It's 20 meters upwards.
So, but it does not rise the whole height, right? It collides somewhere in between.
But that is in the ground frame, no beta. In A's frame, what is happening? You understanding the point now? In A's frame, the ground is also coming closer to him. You understanding? What is the object A is seeing? That the ground was here at t equal to 0 and B was here. Okay. And after that much time, now the ground has reached here and the B has reached here. Got it now?
Yes, sir.
So now that we know that in 1 second in A's frame, this is what happens. So back to in ground frame. This is where they were at t equal to 0. So at t equal to 1 second,
So we can subtract it from 20.
Yeah. So you can also verify that at t equal to 1 second, the magnitude of A's displacement plus the magnitude of this B's displacement should be equal to 20 meters. So we could have also calculated the question this way actually, but that would be in ground frame. See, this is giving us the same result ultimately. Okay, now let's look at an example of a two-dimensional problem with this application, where the whole thing becomes a little more interesting. Now this ball A is dropped at time t equal to 0. And this height 60 meters. Now simultaneously from here, somebody kicks a ball like a football or something. So B is projected at t equal to 0. Now B's projection velocity like this, and B is projected from a point which is at a horizontal distance like this of 80 meters. From here. So given that this projection speed is 50 meters per second and the angle at which it is projected is 37 degrees. So first of all, show that B collides with A, and find the time and position of this collision. So once again, what you can do is you can solve both of these in ground frame. You can see that basically should happen is that at some time t, A should have dropped here and B should have reached here simultaneously. Okay, but it's going to be much easier to solve if we look at the motion of one object with respect to the other. Okay, so And that will be which type of motion? It will be a uniform motion or unaccelerated motion. Okay.
One
So
minute.
let's start by understanding that if we use a common reference frame like this, so in this reference frame at some position like this, B has been projected like this at t equal to 0, and simultaneously A has been dropped at t equal to 0. Also, this triangle formed by A and B and the vertical and horizontal lines, they have, that triangle has 60 meter and 80 meter. So you can see that initial velocity of A is 0. Initial velocity of B is, so U is 50 meters per second and theta is 37 degrees. So when you work this out, you can see that the x component will be 40 and the y component will be 30. So now this shows us that the initial velocity of B with respect to A will be 40 I cap plus 30 j cap. Okay. And we know that because the relative acceleration is 0, this is 0. So therefore, the motion of B relative to A is a uniform motion with constant relative velocity. Okay. Now, if you look at this relative velocity, now what is the position of B with respect to A initially? That is this vector. Now, initially at t equal to 0, the position of B with respect to A, as you can see in the diagram, is minus 80 I cap minus 60 j cap. So you can see that the direction of the vector VBA is directly along the line BA. It is opposite to the position. Sorry, this is not displacement, this is position. So we should denote it with R. So therefore that shows that they will collide. So what this implies now, that in A's frame, B will move along the line PA, colliding and hence collides with A. So what will happen is in A's frame,
Sir,
yes,
sir, RBA should be minus 50 I cap minus 60 J cap.
it should be minus
50.
80, na? I cap minus 60 J cap. This only, na?
The horizontal distance is 50 meters.
No, it's given as 80, na? See,
Okay, okay.
otherwise they will not collide. If it was 60 and 60, they would not collide because
No, I read as 50.
okay. So with respect to A at t equal to 0, B is like this and the ground is like this. And B is now moving such that the relative velocity is directly in this direction. So at some time t in A's frame, the ground would have come closer somewhere and B would have reached here. So you can see that this distance is how much? It is 100 meters. And the magnitude of this relative velocity is how much? It is 50 meters per second. So the time taken so they should collide at 2 seconds. Now, once you've understood that they collide at 2 seconds, you can calculate the position in the ground frame when they collide. So this is where they collide.
So we can also use the equation of trajectory to prove that the trajectories of A and B intersect, right?
Exactly, you can do that also. Okay, or for example, you can also solve time-based equations. Okay, that individual with respect to ground frame, it should be such that when B's horizontal displacement becomes 80 meters, at that point of time, B's vertical position should be such that B's vertical position plus A's vertical displacement added together should be 60 meters, so that they are at the same position vertically. Okay, but those involve like little bit more calculation compared to this. This is, you can see, the easiest method.
Yes, so I tried in that method, but I'm not getting the answer. Like I'm getting time as 1 and 5 seconds.
No, you'll get this only. Okay, so let's see. So if you solve this in the ground frame like that, okay, then you can see that at an instant when A has fallen down through a displacement SA of magnitude half gt square time t. So it simultaneously at this point of time, what should happen? B was here at t equal to 0. Should reach here. So B's x component of displacement is u cos theta t. So that is 40t. And B's y component of displacement, so that is equal to 30t minus 5t square. So when they are colliding at that point of time, so xp is equal to 80 meters at t equal to how much time? So 40t should be equal to 80. So t is equal to 2 seconds. Now at that particular time, yv will become 30 into 2
40 meters.
minus 5 into 4. You see that this will become 60 minus 20, 40 meters. And at that same point of time, what is A's downward displacement going to be? Half
So it
into
will be
10,
20.
so it's 20 meters. So you can see that at t equal to 2 seconds, B is vertically below A's initial position. Okay. And that too, it is 40 meters above ground. Okay. And A has dropped 20 meters. So you can see that magnitude of SA plus YB is 60 meters. So they are at the same position. Okay, so hope this is also clear. But as you can see, this involves solving an accelerated 2D motion for B and then comparing it with the motion of A and all that. So it is like a couple of steps more complicated than the relative motion method. So especially at the exam level, when you want to solve things with the fastest possible method, you just remember this as a trick. Anytime you're solving the motion of two particles which are in projectile motion or motion under gravity, here you won't say exactly that A is in projectile motion because it's in free fall, but importantly, both are moving under the action of gravity. So their relative acceleration is zero.
So, sir, when the question involves two or more projectiles like this, so this is the fastest method to solve it.
Yeah, exactly. Okay. Now let's move on to one final concept related, or one final concept as part of relative motion, and that is the concept of relative velocity of approach or separation, as may be the case, okay, between two objects. So this is a little bit different as a concept compared to relative velocity itself. Okay, so this we denote it with the symbols V approach or V separation. So the idea is like this, that for two particles or objects in motion, if at a given instant the distance between them is either reducing or increasing, then they have an instantaneous. So the term instantaneous means that it is at that moment. It might change after a while. Okay, they have an instantaneous approach or separation velocity. So this approach or separation velocity is the instantaneous rate at which the distance between them decreasing, or increasing. So what we mean to say in general is that imagine we have two bodies, A and B, or two particles A and B, which are moving in some way like this. At this given instant, they have some velocities VA and VB. So now you can see that from the way they are moving in this diagram, you can see that this is suppose at some time t, there's a distance s between them. Now after some time, A would have reached here, B would have reached here. So in this case, at some time t equal to delta t, or t plus delta t, the distance between them has decreased. From s minus delta s. So in this case, A and B have an approach velocity. But it could be another situation where, let's say, A is moving like this. Let's say B is moving like this. So now what is happening is after a time, the distance between them is increasing after some time. So here they are separating. They have some separation velocity. Here they have some approach velocity. The next thing is to be able to calculate this given the individual velocities, how to calculate the approach or separation velocity. Okay. So just make a note of this definition first of approach or separation velocity, then we'll see with a series of examples, we will develop the formula of how to calculate this approach or separation velocity.
Sir, after doing this concept, can you also show an example where we involve two projectiles and calculating the time at which they collide and all those things?
Yeah, we will see. So in your module in kinematics 2, that is module 1, there is a chapter called kinematics 2 after kinematics 1. So in that, there are some good problems in the in-chapter exercise as well as in the main exercise at the end of the chapter. Okay.
Yes.
So a lot of relative motion problems are there that which involve that kind of situation. All the situations we've discussed actually, the relative motion between falling rain and a moving observer, or a swimmer moving in flowing water, as well as two projectiles. Whereas comparatively, H.C. Verma has less number of problems of relative motion.
Yes, sir. Only 6 to 7 problems are there.
The problems are good, the ones they have, but the number of problems is less. So at this stage, you can use the module kinematics 2 as the main reference material for doing questions of relative motion. Okay, so now let's understand this relative approach and separation velocity with some examples. Now we'll start with a very simple case where you have A and B as two objects which are moving along a straight line, and that too, their line of motion is directly the line joining them. That situation is very easy. So for example, here, if we have a situation where A is moving like this and B is moving like this, it's very obvious that they are approaching each other. For example, if VA here is 10 meters per second and VB here is, let's say, 8 meters per second. and the instantaneous distance between them is s. So in this example, we can see that BA plus BB is minus of ds by dt, is the rate at which the distance s is decreasing. So the approach velocity between them is directly equal to 18 meters per second. Because it's very easy to understand, because after some time what will happen, E would have come closer to B by 10 delta t, and B would have come closer to A by 8 delta t. So overall the distance between them has decreased by 18 delta t. So the rate at which the distance is decreasing between them becomes 18, okay, it's meters per second. Now let's say we have a situation like this, where E is moving at 10 again like this, as in the above case, but B is this time moving away from A. Now again you will see that while B is moving away, but is moving away at 8, whereas A is moving in this direction at 10. So overall what happens, the distance between them is decreasing with time. So this time also the rate of change of this is a negative rate of change, and that is equal to BA minus VB, or the approach velocity this time is 2 meters per second. But likewise, for example, if you have a situation where A and B are moving in opposite directions, then you can see the distance between them is increasing with respect to time. They're having a separation velocity of 9 meters per second. Whereas suppose it is like this, that so here they're having a separation velocity of 2 meters per second. So this is set of examples involving one-dimensional motion along a straight line for both the objects. And in that, using relative motion concept, we are looking at instantaneous approach and instantaneous separation velocity.
So can you please hold up for a moment?
Yeah.
Yes, sir.
Okay. Now let us look at the more interesting situation where the motion of A and B is not directly along the line joining A and B. Okay. So for example, if we were to have a situation like this where at the given instant this is how the velocities are. So this is having some velocity VB, but at an angle of theta. Whereas this one is having a velocity directly towards this. So here we can see that what we can do is we can break the motion of B into two components. So this VB cos theta is contributing to the distance between them is denoted by an X factor, okay, like this. So you can see that VB sine theta here does not contribute to rate of change of X. You can see that if we have taken this as our X axis, then the distance between them S. So if A is at some X coordinate XA right now, and B is at some X coordinate XB right now, you can see that the distance between A and B is XB minus XA. So the rate at which this distance is changing should be, so it should be rate of change of B's X coordinate minus rate of change of A's X coordinate. Now you can see that A's velocity is BA I cap. So that means that is the rate at which A's x coordinate is increasing is plus BA. But B's velocity is minus VB cos theta I cap plus VB sin theta j cap. So this one is the rate at which B's x coordinate is changing, and this one is the rate at which B's y coordinate is changing. But that is not important to us. What is important to us is the rate at which B's x coordinate is changing. So from this you can see that the rate of change of B's x coordinate is minus VB cos theta. Whereas rate of change of A's x coordinate is plus VA. So now you substitute both of these in this. So you can see the rate at which the distance between A and B is changing, ds by dt, is this minus VB cos theta minus this, so that is VA. So it is negative of VA plus VB cos theta. So the rate at which the distance between them is changing is a negative quantity. That means they have an approach velocity. So the approach velocity between them at that moment is VA plus VB cos theta. At a very simple level, it is the component of A towards B plus the component of B towards A. So the approach velocity, in this case, VA plus VB cos theta, which though I proved this using this calculus sort of method here, you can understand it is very simple. This is the component of A's velocity directed towards B at that moment. And similarly, this one, it is the component of VB directed towards or pointing towards E. Okay, so just make a note of this situation. Okay, so now let us see how this concept of, actually before that, let's look at a more general case also. Okay, so if, for example, we have a situation like this where E has an instantaneous velocity, is making an angle alpha with the line AB like this, and B has an instantaneous velocity like this, then the approach velocity is the rate at which S tends to decrease with time. So it will be the component of A's velocity directed towards B. So that is VA cos alpha plus the component of B's velocity directed towards A, which is BB cos beta. So as a numerical example, let's see this now. So first thing here is, are A and B approaching or separating from each other at the given instant, and accordingly find the approach or separation velocity, whatever might be the case. Okay.
So it will separate V approach and V separation along X and Y axis, right? Respectively.
Yes, very good. That's correct. They have an approach velocity because the component of A towards B dominates. Okay. So you can see that they have an approach velocity of, in this case, BA cos 53. But this one is actually moving away. So it's minus VB cos 37. So this will be how much? It will be 3 into cos 37. So that is 4 by 5. 12 by 5.
So it should be 3 minus 2.4.
Oh, yes, that's correct.
So V separation dominates.
No, approach dominates, na, because this is 3. See, this component that A has towards B, this is how much? This is 3. But this component that B has away from A, that is,
No, sir, I'm talking about the Y components.
Y component doesn't come into play over here, na, because right now A and B are lying on the x-axis. You understand me? So the perpendicular component does not contribute to the instantaneous approach velocity.
No, sir, I'm just trying to imply that the separation velocity is more than the approach velocity.
No, that is not the case, na, but they are actually approaching each other. The distance, see, two objects cannot simultaneously have separation and approach. You're understanding the point? They are either approaching each other or they are separating each other from each other, because the distance between them at the given moment is either increasing or decreasing. No, is the point clear?
Yes, sir. I was just telling that the velocity of separation along the y-axis is greater than the velocity of approach along the x-axis.
That is what I'm explaining over here, beta. The component of velocity along the y-axis is not a separation velocity. Separation velocity is in which case when the distance between the two objects is increasing, we say they have a separation velocity. When it is decreasing, we say that it has an approach velocity. So the y component of velocity is not a separation velocity. Is the point clear?
Yes, sir.
If we had a situation like this where two objects are placed such that right now they are oriented in along, let's say, the y-axis. Now in this case, what would happen? The y component of velocity would contribute to the approach or separation velocity. Now suppose this is a situation where this has a velocity of, let's say, 4 meters per second at an angle of 60 degrees like this, and this has a velocity like this of, say,
So
2
in this
meters
case,
per
the
second
y component will dominate, right?
at 37 degrees. Okay. Now in this case, what would happen? It is the y components of velocity which are going to decide whether they are approaching or separating. But you can see in this case, B is moving directly away from A with a component of how much? 4 cos 30. So that is 2. Whereas A is trying to move towards B with a component directed towards B of how much? 2 cos 37. So that is 1.6. Okay. So now which is dominating? The separating velocity of B is dominating. Okay. So here the separation velocity between A and B would be equal to VB cos 60 minus VA cos 37. So in this case, they would have a separation velocity, not an approach velocity. And the instantaneous separation velocity would be this. So the instantaneous distance between them is s. Then ds by dt is a positive quantity. Here, the distance between them is s. Then ds by dt is a negative quantity. So minus of ds by dt is 0.6. Okay.
Yes, sir, I got it.
Okay, now next up, let's look at some more applications of this concept of approach and separation velocity. Now, one of the places where we can use the concept of approach and separation velocity is in developing constraint relations, the type you have seen probably in Newton's laws chapter. So application of approach velocity concept for constraint relation type of problem. So during the motion of this system, at some instant, if theta is equal to 60 degrees and PB at this moment is 2 centimeters per second, then find the speed of the block A at the same instant. So this is something where we can very effectively use approach and separation velocity concept. Though till now you would have been used to using calculus, which will make this a little bit more complicated. So take down the question first, or at least the diagram, and we'll understand immediately. Yes, very good. That's correct, Kirti and Anirudh. Okay. Now we'll see here how we can use the concept of approach and separation velocity. So if we take the distance of this point A with respect to this point, let's say P, if we take this distance as S, okay, and then we take the distance of this point Q with this point B as, let's say, Y or what, okay. Now we can see that S plus Y should be constant. This is thread length conservation. So that means the rate of change of ds by dt plus the rate of change of dy by dt should be 0 because the sum of s and y is constant. Now, if you look closely, this point A is moving like this with the velocity va. So this quantity ds by dt is such that s is decreasing at the rate of the approach velocity of A towards the point P, which is how much now? It is va cos theta. And this quantity y is increasing at the rate which is equal to the separation velocity of B from the point Q. So that is equal to plus VB. That's equal to VB. So what this tells me is that S is decreasing at the instantaneous rate, PA cos theta, and Y is increasing at the instantaneous rate, plus VB. So now substitute in this. Yes, you can see this is a very simple and direct way of doing this type of constraint relation problem.
Sir,
Yes.
sir, in the module there is another heading called under the name relative projectile with variable acceleration.
Yeah.
So you'll be doing that in the next class, or
Yeah, we'll discuss that as problems because we have already discussed variable acceleration in the calculus section. Okay. So we'll just look at as an application of that. Okay. Next, we will look at another example of the application of relative motion concept, or rather approach and separation velocity concept. Now, this is a very specific kind of situation. Okay. So what we have is that three particles are located at the corners of an equilateral triangle, and they simultaneously start moving at time t equal to 0, such that they are always chasing each other. Okay, so A has a velocity vector which always points towards B. B has a velocity vector which always points towards C, and C has a velocity vector which always points towards A. So this is where they start from at t equal to 0. With velocity vectors such that they are always targeting the other particle. So A, B, and C start moving at time t equal to 0, such that A's velocity always points to B. B's velocity always points to C, and C's velocity always points to A. And they move such that the magnitudes of their velocities are uniform. Okay, but the direction is always changing. So we have to find the time t at which they collide. It's, as I was telling you, this is a very specific situation where, because particles are chasing each other, like heat-seeking missiles will always chase the target based on the heat signature of the target. So like that, each of these particles is always trying to home into the other one, or it's chasing it with a velocity vector pointing continuously at the other one. So from that fact and from the symmetry of the problem, we'll see that simultaneously all three of them will collide at the centroid of this equilateral triangle. So let's calculate the time for that to happen. So before calculating the time, we have to understand the couple of basic things about the motion. So let's start visualizing the motion, okay, to understand how exactly they are moving. So at t equal to 0, if they are located as discussed like this, but having velocities pointing in these sort of directions, all of magnitude V0. So now if we try to understand where these particles are located at a very short time later, like a very small amount of time delta t. So A would have moved to this position by then, let's say. B would have moved to this position. C would have moved to this position at t equal to delta t. So now what will happen is that they are still forming an equilateral triangle, but slightly smaller in size. So their velocity vectors will accordingly now turn like this. So now a little bit later, they would be located like this. forming an even smaller equilateral triangle. And again with velocity vectors having turned. So like this, they will follow individual paths. They are somewhat like this. And eventually collide at the centroid at some time t. So now if we look at any general time t in between, let's say A is somewhere here, B is somewhere here, and C is somewhere here at that time. Symmetry will show you that this will still form an equilateral triangle. At any instant of time. And still their velocities are such that B is moving towards C. C is moving at 60 degrees to this line. A is moving towards B like this. So what we can see here is that at any instant of time, whether we are looking at t equal to 0, or we are looking at some time t, let's say. Okay. So at this time, A and B have an approach velocity, or for that matter, B has an approach velocity towards C, or C has an approach velocity towards A. So all these three quantities are equal to V0 plus V0 cos 60, or 3 by 2 V0. Now at some later time also the same thing is happening. The triangle has changed geometrically, it becomes smaller, and the angle, and I mean it's turned and all that. But if you look at the three particles with respect to each other, they're still in that same situation. So still they have the same approach velocities. So this statement holds true always till they collide. So their approach velocity, if at some instant the distance between any two of them is s, so minus ds by dt is equal to 3 by 2 v0, which is a constant. So when this is a constant, this can also be written as minus of delta s by delta t. So at t equal to 0, the distance between them is L, and at some time t, if you want to calculate, the distance between them is 0. So from here to here, the change in distance is minus L, and the change in time is t. So you can see that L by t should be this approach velocity. So the time at which they collide should become 2L by 3 v0. So as I was telling you, this is a very specific type of question where we use approach velocity concept in this case, because while the particles are having complex motion and complex type of path in the ground frame, but if you just concentrate on their motion with respect to each other, they are moving in such a way that their approach velocities are remaining constant. So they're always coming closer at a uniform rate of 3 by 2 v0. So it's easy to find the time at which they have completely closed up on each other from an initial distance of L to 0. Okay. So make sure to revise this concept of approach and separation velocity carefully along with relative motion of projectiles. Okay. We will look at more questions in the next lecture, and especially questions from the module, as well as the last few questions from H.C. Verma, which also use relative motion. Okay. So thanks for attending and have a nice day, all of you. That's it for today.
So,
Yes.
so can you explain that at t is equal to 0, s is equal to L?
Sorry.
So can you explain the statement that at t is equal to 0, s is equal to L?
So that you can see in the diagram on the left hand side. Na? At t equal to 0, they are on the corners of an equilateral triangle of side length L. Na? So what is the distance between any two of them? It's equal to L.
Yes.
Whereas whenever they are colliding, that's happening at the centroid at some time t. So at that time, the distance between them has become 0.
Yes. Yes.
Okay, so the distance between them is changing from L to 0. So they've approached each other by a distance of L at a constant approach velocity. So that L by T should be equal to that constant approach velocity.
Thank you, sir.
Thank you, sir.
Okay, people.